Okay, so this is a problem from the book Concepts of Physics written by HC Verma. So this is the chapter heat transfer and the question number is 5. Question number 5 from the exercises. The situation given in the question is basically this box provided to us which contains water, and the box is being heated. Okay, and as you can see, these water vapors are produced. Okay, these are water vapors produced. Now, okay, so in this container the water is boiled and the area of the bottom of the container is given to us, right? The area of the bottom of the container is given to us, and that is given, that is 25 centimeters square. All right, the thickness, that is this, is given to us. This length L is 1 millimeter, and thermal conductivity is 50 watt per meter per degree Celsius. 100 gram of water is converted into steam per minute in the steady state after the boiling starts. So in the steady state after the boiling starts, it has been said that 100 gram of water is converted into steam per minute. So what does this mean? 100 gram of water is basically 1 by 10 kg of water. So in the steady state, 1 by 10 kg of water, which is in the liquid form, is converted into steam, right? Initially, which was in the liquid form, is converted into steam. At the steady state, what is happening? At the steady state, at a steady rate, the water would be evaporating, because at the steady state, a steady heat current will flow into the container and into the thing is contained in the container, which is water in this case. So the amount of heat that goes into this container per unit time would be equal to the amount that leaves the container per unit time. And how does the heat leave the container? It leaves the container through the water molecules. Well, as you can see over here, let me use a different color. Over here, these were the water molecules on the surface. Now they have gained heat energy, and since energy is conserved, it is given in the question that no heat is lost to the surroundings. So this is the only system that we need to consider, right? So whatever amount is given into the container, that same amount will go out of the container, and it will go out through these water molecules which lie on the surface of the whole bulk of water. Now they will get the heat, and they will get enough kinetic energy to leave the attractive pool of the water molecules that lie in the depth of this water bulk, and so they will be able to move out of the container in the form of water vapor. So whatever amount is coming in goes out in the form of water vapor. So that, well, I made a mess out here in case of this drawings. Let me clear out this first, and then we'll continue with the question. So I think you've got a basic idea, right, that whatever heat is coming in is going out in the form of water vapor. Now what does this mean? This means that we have got the heat current, right? We have got the heat current. Let me change my color. I'll take green. So the heat current, it will be the amount of heat gained by the water vapor, which we can obviously calculate by ml, where L is the latent heat of vaporization of water and m is the mass of the water involved, divided by T. All right, so we can basically do this calculation, right? Though as I told you that the mass of the water is 1 by 10 kg, and the latent heat of vaporization is given in the question, we need to take the value 2.26 into 10 to the power of 6 joule per kg. So we can multiply this two, and then we get ml, which is 2.26 into 10 to the power 5 joules. Now we need to divide by 60, right? 60 seconds, because we are taking it out in joule per second, and per minute this much of mass sorry, this much of mass is converted, so per second, for per second we'll have to just divide by 60. So by doing this we can calculate the heat current. So we got the heat current, right? And now we can, now I think I can remove this diagram to make out space. Okay, so I can have more space. All right, so we basically get this value, right? And the value comes out to be 0.38 approximately, or you can write this as 3.8 into 10 to the power 3, right? You can write it as 3.8 into 10 to the power 3 joule per second. Okay, so this is the heat current given to us. Let me put that inside a box. Let me choose the color. Okay, now I'll put it inside a box. Okay, so this is the heat current basically, right? This is the heat current that we have got. All right, now what do we need to do? Now since we got the heat current, we can do the rest of the calculation. Now what do we need to find out? Assuming that no heat current is lost, calculate the temperature of the lower surface of the bottom. Yeah, now we need to calculate the temperature of the lower surface. Well, we know this formula that heat current is equal to conductivity of the material into area of the material through which heat is passing divided by the length of the material, right? Perpendicular, parallel to the flow of heat, and the change in the temperature, right? And if we find out the change in temperature, we can get our answer. So in place of this Q by T, we'll use this value which we calculated. The value of K is provided to us, the value of A is also given to us, and L is directly given to us. So all these three, only we needed to calculate this part. Rest, these were provided in the question. And so after doing all the calculations, what do we get? We get the change in temperature to be equal to 30. All right, it might be now 30 kelvins or 30 degrees Celsius. It doesn't matter because it's the change, right? And the conversion factor between Kelvin and degree Celsius is only like 273. Okay, this number. So if you're converting from Celsius to Kelvin, you have to add this, and if you're converting from Kelvin to Celsius, you have to subtract this. So the overall subtraction simply eliminates this 273, and so it can be either of these units. Okay, so that's the change in temperature. Now we know water boils at 100 degrees Celsius, right? All right, now let me explain this thing qualitatively to you. I want to explain this thing qualitatively. So we got delta T to be equal to 30, and it can be at Kelvin or degrees Celsius. Now since water boils at 100 degrees Celsius, and we have got actually, let me use the previous color which I used. Okay, so I got this utensil before, right? So here we had the fire, right? We had the fire at the bottom, so there was fire out here, and so we can say one thing, that we can actually find out like the temperature of this bottom surface, which we need to do, by the way. And so I have just completed this drawing again. Okay, so since the change in temperature is 30 degrees Celsius, right, and we need to calculate this temperature over here, and we know that the temperature at this part is how much? Is 100 degrees Celsius. How do we know that? Because temperature at this part is primarily like just it's primarily water vapor. This part is simply water vapor, so it has got to be 100 degrees Celsius. It's simply water vapor, nothing else, right? So it has got to be 100 degrees Celsius. So this change in temperature is simply this, right? And so I'll just write this down. change in temperature minus 100 degrees Celsius is equal to 30 degrees Celsius, right? Because obviously this temperature would be more at the bottom, right? It's heat is coming from here, I mean heat is coming obviously, so here the temperature would be more, 100%. So T is equal to 130 degrees Celsius, there's no doubt about that, right?